show. That's why we created a special Marshall McLuhan walking tour, which you can download at the Spark blog. If you find yourself in Toronto, you can walk through parts of the city that were important to McLuhan, hear interviews, ideas, and sounds of the city. If you're anywhere else, you can still join us on our sonic adventure. We've got an online map with photos and audio, so you can follow along digitally. You look to the world differently, and you can too. Find it at cbc.ca/spark/McLuhan. This is Spark from your friends at CBC Radio. What does new technology make obsolete? My mind immediately jumps to older technologies. Nice, shiny swords meant warriors could put away their wooden clubs. The invention of the automobile dealt a nearly fatal blow to horse and buggy sales. And digital technology is making all sorts of stuff obsolete and disrupting whole parts of the economy along the way. How far could it go? What if one day digital technology could replace our very own grey matter? That's right, our actual physical brains. It's been a topic for debate in philosophical and artificial intelligence circles for a long time. So let's wade into those heady waters and take a little swim, shall we? Anders Sandberg is a researcher with the Future of Humanity Institute at the University of Oxford. He's been studying the possibility of making copies of the human brain. It's called whole brain emulation.
Well, that's a long-winded way of saying simulating everything going on inside a brain in a computer.
Like memories and feelings and everything?
Well, that is the aim. When we talk about simulating something, it's just supposed to look like what we're simulating. But an emulation is something that's supposed to do exactly the same things as the original. So if it really is an emulation, it should have memories and emotions.
So this technology doesn't exist yet. Why do advocates of this type of research think it's even possible to do something like this?
Well, we've already done pretty nice simulations and emulations of very simple nervous systems. So the earliest was done in the 1940s that simulated just a part of a single nerve cell, and that was done by hand with an electromechanical calculator. And today we have computer simulations of fairly complex systems, like the swimming motions of a lamprey. It's a very simple fish, and we understand how it's doing its swimming quite well. Parts of how crayfish swallow. And we have even pretty big simulations of several millions, even up to billions of nerve cells running on supercomputers.
So from the point of view of artificial intelligence, basically what you're trying to do is model neural networks. You're not trying to make like an algorithm of how a brain thinks, right?
Yeah, there is a difference between understanding a brain and just running it. And we might one day have a nice theory about how emotions or memory or consciousness work, an understanding of what's going on. But that's not the same thing as being able to do it. And similarly, we might be running all the little details of a brain without actually understanding how they produce that kind of thinking, that kind of activity. So this is an attempt at using brute force instead of trying to have a nice theory about the brain.
But what about the importance of the body? I mean, it seems to me that it's because we're embodied that we know the world around us in the first place, and that we understand things like context and we learn and so on.
Yeah, I think we definitely need to have a simulated body connected to the emulated brain. After all, when I speak to you, I'm actually sending nerve signals that go to the muscles of my lungs and my throat, producing sound. When I'm looking at something, even on a computer screen, I'm moving my eyes around. We would need to actually have simulations of eyes, lungs and muscles to some degree in that system.
So would that be anything like being actually like a sentient being, though, having a simulated body?
I would bet that we would find that an emulation would be sentient. I have colleagues who disagree with me about this. So I think the best way is actually to try to find it out. It needs to be a good enough body to actually interact well with the surrounding world. But that doesn't necessarily mean it had to be exactly accurate. We tend to be surprisingly well fooled by a lot of simple virtual reality tricks.
Yes. Anders, I don't want to take us down too much of a philosophical wormhole here, but can you just explain what is being presupposed about what a mind actually is by assuming that you can do this kind of thing?
Well, the main presupposition is, of course, that minds are linked to the functions of the brain rather than the stuff the brain itself is made of. There are some people who say that, no, minds need to be made out of carbon, water, and all the other things we have inside our heads. So anything that we're doing the same kind of processing, but was doing it in silicon, would not be having a mind. On the other hand, functionalists, and I think I'm calling myself a functionalist, think that no, it's the function. A calculator is indeed adding numbers, but it's doing it in a very different way than I'm adding numbers. But the function is the same. And this is, of course, a quarrel that's been going on for a long time in philosophy. And I don't think philosophers are going to solve it. But, well, if we get a brain emulation and it actually works, I think that would be able to settle it.
So you actually finally have an answer to a philosophical problem.
Hopefully, yes. I could imagine taking us uploading skeptic and uploading him into a computer, and then we ask the brain emulation, do you change your mind? And after a while the computer says, yes, indeed, I'm feeling conscious actually in here, so please don't turn me off. I recant my previous philosophical view.
But I guess it does raise the question of, indeed, what consciousness is.
Yeah, and people have a lot of very different views on that. So some people say that there's some deep property that you really need a particular kind of organizational matter to do, and maybe silicon can't do that. On the other hand, functionalists would say, well, consciousness, well, whatever it is probably something that can be run as an algorithm. And people have very different views on this, and it's called the hard problem of consciousness, not for nothing.
Yeah.
It's very hard to understand even what we're talking about when we say that something is conscious.
So what do you think some of the ethical questions might be in a world of emulated brains, assuming we get there?
Well, first of all, if they work as our brains do, they of course have the same kind of rights. We should be treating them like people. They just happen to be software people. But that's always going to be a kind of civil rights problem. But I think a more deep and interesting one is when you start making copies. After all, if you have something running on a computer, you could just make a copy of that information and run it on another computer. And now there would be two versions of the same program.
Right. If there are 3 or 4 or 5 or 500 versions of Nora, are they all me?
That's a very good question. Again, philosophers have been having great fun with the personal identity, and there are various different answers to the question. Some people say that, well, numerical identity, one being can only be one being. So those copies are not you. On the other hand, I think you would all find that you have the same memories and agree with each other on most things, at least initially. Over time you would start diverging, of course. My own personal view is that, well, all sufficiently Nora-like processes in the universe, they're Nora.
Death, of course, is a part of nature. How would this technology change the rules of the game?
Well, first of all, we would, of course, be able to make backup copies, which is really good because, well, we do tend to get run over by cars or get old and sick. But it also leads to interesting problems when you could actually have a skilled professional who likes working and he makes several copies of himself. Now can do much more work. And he might even be underbidding everybody else.
It really lends a whole new urgency to the importance of backing up your computer, I suppose, if you think of it in that way.
Oh, yes, and we tend to forget to back up our computers, despite that they contain very precious digital possessions like family albums. So I'm really hoping that in the future we are sensible about backing up our minds. But I'm fearing that we're going to discover the hard way that occasional backups are not quite as up-to-date as we would like to.
So if you were a betting man rather than an academic, do you think this is actually going to happen?
I would bet about 1 chance in 4 of having brain emulations somewhere around the middle of a century. So I would probably not be betting money on the emulation, but I would be trying to figure out how to invest my money in some company doing brain emulations.
Anders, thanks so much for talking to us. Fascinating.
Thank you.
Anders Sandberg is with the Future of Humanity Institute at the University of Oxford. I had a longer conversation with Anders about the prospect of many, many Nora brains stored in many, many places. You can find our full conversation on whole brain emulation at our blog, cbc.ca/spark. Now, as Anders said, the day when the world can have many complete Nora brains dreaming up new ideas for Spark is still, if it's possible, a ways off. But other combinations of human grey matter and technology are not so distant. At Toronto Western Hospital, research is underway to develop a microchip implant for the brain that would treat epilepsy. If all goes well, the chip could one day make epileptic seizures obsolete. I was curious, so I headed off to the hospital. Dr. Peter Carlin is a neuroscientist who runs the lab. Hello, Peter.
Hi.
Hi, it's Nora.
How do you do, Nora?
Nice to meet you.
Welcome.
So where did the idea of putting a microchip in the brain come from?
I think that's been around maybe in science fiction for 50 years or something, and we've been talking for several years about making microchips that we can stick into brain and they'll be wireless. So the exciting thing is, first of all, new ways to understand the signals of the brain, and the other thing is then to figure out ways to stop seizures if possible.
So what's the best case scenario in terms of somebody who has epilepsy down the road having one of these chips in their brain?
Well, this is, well, I would hope that this might obviate some types of surgery where we take out brain tissue. In other words, we might be able then just to stick these chips in and they can locally control the local tissue if and when it started to go into a seizure. So that would be an ideal scenario. But another important thing would be even to know when a seizure is going to happen and alert the patient with an alarm or a phone call to the parents, or so that sort of thing is also possible. We're very early days, so we're just starting to think of what's applicable.
So can you show me the lab?
Yes, I'd be glad to.
Let's go. Peter introduces me to Roman Genov, an associate professor of electrical engineering from the University of Toronto. Roman's working on the microchip's physical design. And when it comes to a chip for the human brain, we're not just talking Intel inside here. Creating a microchip that interacts with brain tissue and signals makes matters complicated.
If you're looking to use this technology to monitor vital signs, you would be really trying to optimize how much heat is dissipated by the chip. So you really cannot increase the temperature of the tissue surrounding it by a lot. Certainly, you would not feel any difference when you touch it that it's warm or not. That's for sure. Another difference is that many of the vital signs you are looking to monitor are very small signals. Neural field potentials or neural spikes would express themselves as voltages in the microvolt level. So microvolt is 1/1,000,000th of a volt, right? And then appliances you use today use 100 volt, so that's the scale. So they should not contaminate the signal that they record. So they should not emit their own noise or any kind of interference that would distort or bury entirely your signal. And I guess functionally, these chips are also different. When you are looking at your desktop computer, you would typically have a processor that would be crunching numbers. And those numbers would typically be digital. We're used to zeros and ones. That is the language that digital processors understand. Whereas the nature around us is analog. So there's no clear black and